1. All right, and again, hi, welcome to Math 234. Today, we're doing a section that isn't the one that's currently on screen because that's a review of Calc 1. But I wanted to start right here because we're going to be upgrading this idea today. So the first sort of major application of derivatives in Calc 1 was locating maximums and minimums. And the method that we had back then was, at least at the start, we would stare at graphs and say like, hey, look, there's the maximum, there's the minimum, because you can just do that with your eyes. But then we started to notice interesting things about maximums and minimums. In particular, that they had horizontal tangent lines, or the derivative at those maximums and minimums was equal to 0. And we tended to call those places critical points because we needed a way to just collect all of them before we decided if it was a maximum or a minimum, because they look the same if all we do is the first derivative. And we also said there were absolute maximums and minimums if it was the largest spot around, or the largest spot in total, instead of just a local maximum or minimum being the largest or smallest point around itself. But I'm getting a bit ahead of myself there because we're not going to do the entire bit today. I just want to bring up one other idea, which is not the mean value theorem, but is instead, where did it go? Where did it go? It's on here somewhere. The second derivative test. So that's the other one that I want to look at. So after we pick derivatives, set them equal to 0, found our critical points, one of our methods for deciding if we had a maximum or minimum, or at least a local maximum or local minimum, was the second derivative test, which is good. A second derivative, which generally shows us the concavity of a graph, and said that if we had a shape that was concave down, right, making this a U shape facing down, think of a downward opening parabola, those shapes had local maximums if I had a critical point. Concave down was a local maximum. Again, this opening down. A little counterintuitive because the negative second derivative corresponds to a maximum, while a positive second derivative corresponds to a minimum. So those are, again, counterintuitive. You would think positive and maximum and negative and minimum, but not quite. Think about what the second derivative is telling you, right? Because it is showing you concavity. So we want to be down for a maximum and up for a minimum. But we only had the one second derivative to look at. Because back in Calc 1, that's all we had. Just one function, one variable. We're now in Calc 3, which is multivariable calculus, so we have more second derivatives. So let's go talk about those. To today's big, important, fun lesson. So we'll define those local minimums, local maximums basically the same way. Except now we're going to have a point A, B instead of just a single X value. But if it is the largest point around, it's a local maximum. And if it's the smallest point around, it's a local minimum. We just have to check in more than one direction now, which sometimes gets a bit complicated. We won't worry too much about the absolute maximums and minimums today. That'll be Monday's lesson. But very similar definition for absolute maximum and minimum. Just if it's the largest point in total, it's an absolute maximum. Or, conversely, an absolute minimum if it's the smallest point in total. So, new critical points that we're going to talk about. So in Calc 1, we looked at the maximums and minimums and said that the thing that they have in common is that at those points I can find a horizontal tangent line because the derivative there is 0. If I'm going to upgrade that idea to Calc 3, our local maximum minimums are going to have a horizontal tangent plane because we upgrade lines to planes in Calc 3. So horizontal tangent planes have normal vectors that are vertical. the only way to have a horizontal tangent line. It's a vertical tangent line. For a vector, oops, sorry, I said that backwards. To have a vertical normal vector. I think I said vertical tangent line. That's not what I wanted. I wanted a vertical normal vector. The only way to have a vertical vector, blah, 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 vertical vector is to have something in the z component, some number over there, any number we want, as long as it's not zero, because both the x and the y components of a vertical vector are going to be equal to zero. If we compare that back to the gradient, which we know will give us the normal vector of some surface, that means that the x and the y components of the gradient must be zero. Or in other words, and it's probably the result you would expect, the x partial and the y partial must both be equal to zero. So we're still taking derivatives, setting them equal to zero. Trouble is we now have two derivatives instead of just one. We've got an x partial derivative and a y partial derivative, and they both have to be zero at a critical point. Which means instead of just being able to set something equal to zero and solve for x, we have to set two things equal to zero and solve a system of equations. So it's a slightly more involved process for finding our critical points. I'm gonna guess two hands means a yawn instead of a question, so I'm gonna move on. Right, so you were looking at the screen for a while, you probably read through the whole bit. Critical points that are not local maximums and minimums are going to be called saddle points. I honestly don't remember if we named them back in Calc 1. But we're going to call them saddle points in Calc 2. Nope, this is Calc 3. I'm going to call them saddle points here because at the point where we have a saddle point, the surface kind of looks like a saddle. Right? Go figure. But if you can kind of imagine what a saddle looks like, you're on a horse. My horse is riding over this way. The part where your legs go is concave down. Your legs go over the side of the horse when you are riding on that saddle. But in the spot where you have the seat back, which curves up behind your back, and I'm not a cowboy, whatever that thing is that you grab onto at the front of the saddle that's up near the horse's head, that part, that also curves up to meet your arms right there, right? So a saddle is concave down in the part that goes over the horse where your legs are, and it's concave up where the seat back and the horse's head is. Roughly, that's what a saddle looks like, and saddle points are going to have a similar shape on our surfaces. So, yeah, there's that super fun description. Anyway, what else do we want to say? The first derivative test ends up being a gigantic pain in Calc 3 because there are too many directions that we have to look at. Back in Calc 1, it was pretty easy to just look left and right of a maximum or a minimum to figure out if it's a maximum or a minimum, right? Increasing into decreasing meant a max, but decreasing into increasing meant a min. But we have way more than just two sides in 3D space. So not a great plan. Instead, we'll rely pretty heavily on the second derivative. And of course, there are now 3 or 4 second derivatives, depending on how you count. Not very good with numbers, so I'm going to say that there's 3. Being the second order double x partial, the second order double y partial, and the second order mixed partial, f sub xy. And we're going to need all 3 to talk about that thing. And here's our second derivative test. Starting into the new stuff. It wasn't in the pre-class video. So we're going to define this value, capital D. Why do we call it D again? It's kind of like a determinant. I think it's probably where the D comes from. But anyway, it's going to be our second derivative test value. And it's going to put all of our second derivatives into one idea. So I'm going to take the straight second order partial derivatives, so the double x and the double y partials, multiply those together. Then I'm going to take the second order mixed partial, or the one where I take one partial with x and the other partial with y. I'm going to square that and take the difference between the two of them, putting the straight second order partials first. That's going to be important because I do want to check whether this number is positive or negative. And just to bring some ideas back from Calc 1 before I get into nuts and bolts of how this thing works, I want to be using the same ideas from the Calc 1 second derivative test. I want to say that I have a local maximum if my shape is concave down. And I want to say I have a local minimum if my shape is concave up. So those two ideas are going to stay the same. And in order to check whether I'm concave up or concave down, well, for the thing to work, I need both directions to agree with each other, right? I need both the x direction to become, say I want a local maximum. Just fix on that for a second. The stuff that's highlighted in green. If I want a local maximum, I'm going to need both the x direction to be concave down, and I'm going to need the y direction to be concave down. It's going to be concave down looking from both directions, which really means I need both my second order x partial and my second order y partial to be negative. But I'm going to argue we only need to check one of them. More on that in a second. Because if I want a local minimum, same thing should happen. I'm going to need both the x direction to be concave up and the y direction to be concave up, which means I'll need both of the straight second order partial derivatives to be positive. And again, I'll only need to check one of them. I have a saddle point. Well, at least one example of a saddle point would be when those two straight second order partial derivatives are opposite each other. But if I'm concave up in the x direction, but concave down in the y direction, that's exactly what a saddle looks like from my previous really great explanation of a saddle. So, right. If they disagree with each other, that's one way to get a saddle point. Now let's come back to look at the nuts and bolts of how that number is calculated, because that'll start to tell us something. So, what we're going to claim is that if I want to have a local maximum or a minimum, I need that determinant value, that capital D, the second order derivative test number. That thing has to be positive. Positive. Doesn't matter if I've got a minimum or a maximum. Won't matter if I want to be concave up or concave down. That determinant value, the second order test value, that thing's got to be positive, or both a maximum and a minimum. And we'll break down subcases beyond that. If that number is negative, I'll have a saddle point. And we'll get to the inconclusive spot in a second, but if it's 0, we don't learn anything. So why does that make sense? Because I think it should. Looking at the way that I multiply all this stuff together, I've got my two second order straight partial derivative terms, fxx and fyy. Those are the ones I'm going to focus on. I'm going to subtract from that the mixed partial derivative squared, which means it doesn't matter what that mixed second order is. I'm going to be subtracting a positive number because it's getting squared. So let's just ignore that term for a second. I'm subtracting a positive number. Focusing on fxx times fyy. If I want this point, if I want my critical point to be a local maximum or a local minimum, I need both of my second order straight partial derivatives to match up with each other. They need to either both be positive or both be negative. Which means if they're agreeing with each other, if they have the same sign, fxx times fyy must be positive. Doesn't matter if the individual numbers are positive and negative. Either I have two positive numbers multiplied together, which is positive, or I have two negative numbers multiplied together, which will come out positive because of a double negative. So that first term must be positive to have an extreme point at all. And then I'm going to subtract away some other positive number, which means like if there's something weird going on in like the rotated directions, I could still end up with a saddle point. But for the most part, I'll just focus on, again, fxx and fyy. And again, because they agree with each other, it doesn't matter which one I check to decide if I'm concave up or concave down, because they should both tell me the same thing. So I could check either the second order x partial to see if it's positive or negative, or the second order double y partial to see if it's positive or negative, because again, they should be the same. But almost all of the text just says, look at the second order x partial, and it bases it all on that. Again, we just got to pick one of them, but it really doesn't matter which one you check. Ta-da. So finally, if this thing comes out to 0, that could be because one easy way to say that this thing is going to come out to 0 is if one of the second order straight partials is 0, meaning that there's no concavity at that point. We might not learn anything. I think we had the exact same result from the Calc 1 second order derivative test, second derivative test. We didn't call it second order back then. Or did we? Don't remember. Back in the second derivative test from Calc 1, if the second derivative came out to 0, the test was inconclusive because we didn't learn anything. We'll have the same idea here. 0 on the second derivative test doesn't tell us one way or another what's going on, which is why we say inconclusive. But more on that later. All right, I have just talked enough. Let's go do a problem. I think we've only got like 3 of them today, so it was worth taking a moment to talk about stuff. So back in 12.6, we had this shape, z equals y squared minus x squared. Based on what we know from 12.6, which was quadratic surfaces, this thing is a hyperbolic paraboloid. Right? If it's z equals y squared minus x squared, I've got one linear term, which means it's a paraboloid. The signs on my 2 square numbers are different, which means it's hyperbolic instead of elliptic. So we are going to have claimed that this thing had a saddle point in the middle of it. Well, now let's show it using the stuff that we just learned. Okay, so the things that I want. I first want to find my critical points, which means taking an x partial derivative and getting 2x, negative 2x. Wow. Very first number, and I already got it wrong. Doing great today. If I want a critical point, I know my derivative should be 0. So I'm always going to take derivatives and set them equal to 0. Which is going to give me the super exciting result of x equals 0. Get that hair out of here. X equals 0. 0. But since it's multivariable calculus, we have to do this problems multiple times. I'll stop, sorry. 2y here should be equal to 0 as well, which gives us y equals 0. Now, generally, we are going to need to be solving a system of equations in order to find our critical points. This particular example is quite easy because each of my 2 equations has only a single solution, x equals 0 and y equals 0. But we'll see in some later problems, we'll have 2 vastly different equations that create a system that must be solved together. But at least for our very first example, we'll keep it tight. We get only a single critical point. It's at 0, 0. All right, so we found our critical point. Now we have to classify it, which means we need our second order partial derivatives. Hi.
The critical point be at 0, 0, 0, the z value.
So would the critical point be at 0, 0, 0? Do we need the z value? I'm going to argue no, we won't. So back in Calc 1, when we were looking for our critical numbers, our critical points, we usually classified them just by looking at the x value. Right, so if we wanted a critical point, we just found the x value, and the y value would be whatever the maximum or minimum was, right? So Calc 1, where we classified critical points by just the x value. In Calc 3, we'll classify our critical points by just the x and y values. And then we'll go deal with the z value eventually. Yeah, but for the classification stage, we only need x and y. Murder? Yeah, solid question. I hadn't even thought about that when I was writing the notes. Right, we have our critical point. We want to classify it now, which means we need our second order partial derivatives. So let's go get them. I'm gonna need fxx, which is -2. Derivative of -2x is -2. I'm gonna need my second order y partial, or fyy, which looks like it's +2. And then also, I'm going to need my mixed partial derivative term, mixed second order partial derivative term, fxy. Doesn't matter which derivative I go to do the other one on, whether I start from fx or start from fy. If I do the opposite derivative, I get 0 in either case. 2x partial y is 0, and 2y partial x is 0. Again, by Clairaut's theorem, as long as we have a nice function, fxy and fyx are going to be the same thing. So technically, that d value should be fxy times fyx instead of that product squared. But again, we're going to assume that we always have nice functions. We are going to only be looking at nice functions for our course. So we'll just square that one term. But I digress. I should go calculate the second derivative test value, which is fxx times fyy minus fxy squared. Splash some color in there. And this thing is going to look like -2 times +2 minus 0 squared, which is -4, notably a number that is less than 0. Because our test value is negative, this thing is a saddle point. Saddle point. And if you believe me when I was arguing all that stuff about concavity earlier, I can check my x and y concavities to see that the x direction is concave down, but the y direction is concave up. So just from looking at those two directions, without having to look at any of the rotated values in between them, that thing must be a saddle point. Because their concavities did not agree with each other. But the best way to really come to terms with all this stuff is just keep doing examples. So let's see another one. So here's some function, x cubed plus 3xy plus y cubed. Identify all of its critical points. Or identify and classify all of its critical points. So same thing we do every problem. Try to take a derivative and set it equal to 0. Starting with an x partial, because we usually read x and then y. This thing is 3x squared plus 3y. 3x squared, 3x squared plus 3y. And that thing is going to be equal to 0. And let's also go look at the other side, f partial y. It's going to look awful similar, 3x plus 3y squared. And that thing also needs to be equal to 0. And I think you can see pretty much right away that unlike the last problem, this one doesn't have super simple, immediately obvious solutions. Right? In the other one, all we had to do is just solve each equation for a number. We found our sole critical point. This time we have equations we got to deal with. So I have a system of two equations, 3x squared plus 3y equals 0, and 3x plus 3y squared equals 0. And I want to solve that system. We have a few different ways of solving systems. The most straightforward and the one that almost always works is substitution. So that's probably the method I'm going to demo on all these problems. So I'm going to solve one equation for a variable or isolate a variable in one of the equations and then plug it into the other one. Starting with the one on the left, because why not? I think I get y equals negative x squared. Right. I can divide the whole thing by 3. So I've got the same coefficient on both sides. Move the x squared over to the right side. Y equals negative x squared. In the Zin, go plug that into the other side. This is a negative x squared equals 0. Right, I'll just do some substitution. And then I have to, solve that other equation. But at least I've only got one variable over there now. So that's a kindness. This is 3x plus 3x to the fourth equals 0. That negative ought to square itself away, right? It's on the inside of a square number. Occasionally, there's some weirdness that goes on with a problem like this. Remember that you don't really want to divide both sides by a variable because that variable could be equal to 0, in which case you brick your problem if you divide by 0. So instead of, because like there's a common x in both things, right? Like obviously I could just divide the 3 away from both sides. I don't really want to divide the x away from both sides because again, that x could be 0. Anytime there's a variable factor, I'd rather not divide it by both sides, but instead factor my equation. So I'll call this thing 3x times 1 plus x cubed equals 0. As opposed to just saying 1 plus x cubed equals 0. If I did that, I would end up missing one of my solutions. Because I should get either x equals 0 or x equals negative 1. All right, from those two factors and my zero product principle, I can come up with those two solutions. Either 3x equals 0, meaning x is 0, or 1 plus x cubed is 0, so x cubed is negative 1, and the cube root of negative 1 is still negative 1. But now that I've got two solutions, right, those are the two numbers that make the y partial 0. I have to go back and make sure that the x partial is also 0. So let's do that. I have two options. One, x equals 0, which means y is equal to negative 0 squared, which is 0, 0. There we go. So I get my first critical point at 0, 0. And for my other critical point, x equals negative 1, I get y equals negative 1 squared. All together, the negative survives. Negative 1 squared. Whoa. At least I caught it before. Yeah, cool. Negative 1 squared. The negative survives, meaning y is negative 1. So I get my second critical point at negative 1, negative 1. Yeah, I hear you. So I've got almost all my stuff. That's actually a total fabrication. I'm done with step one of one of these find all the maximum minimum problems. I've done all of the first derivative work. And these classification problems have two steps. One is the first derivative step, the other is the second derivative step. The first is find the critical points, the second is classify the critical points. So I need my second derivatives, my second order partial derivatives. So fxx, if I bring it back up so that it's on screen, just barely. Take another derivative with respect to x of that equation on the top left, and I get 6x. Go get the second order y, or second order double y partial, and take a derivative with respect to y of that equation on the top right, and I get 6y. And then go get the mixed second order partial derivative. Again, I can work from either of my two equations, just take the opposite partial derivative. I get 3 both times. Because 3y partial y is 0, and 3x partial x is 0. Or rather, 3x squared plus 3y partial y is 3. I said 0 because I'm really not very good with numbers, but ignore that part. It's definitely 3. 3x squared plus 3y partial y is 3, and 3x plus 3y squared partial x is also 3. Right? I'll get the same thing no matter which one I go from. So we're only working with nice functions. But that will let me put some stuff together, finding my second order, or my second derivative test values. At my two critical points, I'm going to look at D, specifically at 0, 0. I wasn't really including all of the detail in the previous problems. It ended up not being necessary. I didn't need to plug numbers in to my D values in the previous problem. This time I do, though, because I have an x and a y that survives the second order derivative process. But this thing ought to be 0 times 0 minus 3 squared, which is negative 9. This is less than 0, which means I have another saddle point. Another saddle point. Well, cool, nothing new there. Let's go look at this D value at the other critical point that we found, which was -1, -1. This time through, I'm going to get -6 times -6 minus still 3 squared. And this time I get something different. -6 times -6 would be 36 minus 9 is positive 27. So because my test value is positive, this thing is a local maximum or minimum. But I'm not done yet because the 27 alone doesn't tell me which of those two I have. Doesn't tell me specifically if that's a max or a min. It just tells me it's one of them. Cool. So let's go figure some other stuff out. If this thing came out to be either a maximum or a minimum, my final step is to decide if I am concave up or concave down at this point. And by looking at both of my second order straight partial derivatives, so fxx and fyy, I argued earlier they should have the same sign because that's the only way for this to come out to be positive. And I see that that is indeed what I have here. Both of those second order straight partial derivatives were negative. Got both. They are both concave down. So if I go look at that guy and look at that guy, both of them were negative. They're both concave down. That means we have a local. The O comes first in local. Turns out I'm not very good with letters either. I have a local maximum because we're concave down. Again, all the text will tell you specifically to just look at the fxx terms, the fxx factor. But really, you can look at either because they have to agree with each other if I'm going to have a maximum or a minimum. It doesn't matter which one you look at. Again, they'll be the same, but only really need to look at one. So how are we doing so far? Make some sense? Awesome. At least only I'm not seeing all thumbs, but I am seeing only thumbs and the upward. There was a concave up or concave down joke there. I'm gonna spare you. Okay, yeah, we're holding it together. All right, this is the last problem for today. So, using that method, the thing that we just did, find the shortest distance from the point 102 to the plane x plus 2y plus z equals 4. Cool. So we're looking to find some minimum value. Let's do it. So what thing am I trying to find the minimum value of? Well, I need to go to the distance formula, which is x minus x naught squared plus y minus y naught squared plus z minus z naught squared. All of that is underneath a square root. And I know some things in here. If I'm looking for the distance between a point and a plane, then that point is going to be my fixed values, the x naught, the y naught, the z naught. That's my point because it doesn't change. But I can have whatever point I want on the plane as long as it's the closest to the point that's fixed. That's what I want to do. Right? My goal is to minimize that equation, which means I'm going to have to take a derivative of that equation, and I don't want to do that because that square root is going to make things a gigantic mess. So the first thing I'm going to say is that if I just look at the inside, which is just everything in the distance formula except for the square root part, this new function f and that distance are going to have the same minimum location. Right? The whole square root will be minimized when the thing on the inside of the square root is minimized. So I'm just going to do find the local minimum of f because it's way easier. And I want to be lazy, so I'm going to just look at that function instead. That's step number one, is just ignore the square root. We'll fix it in post. The other thing I want to do is make sure that my function is a function of two variables. When we've been doing all this stuff, we've only looked at x partials and y partials. So I'm going to replace z with what I know from the plane. Basically solve that equation, solve that plane equation for z equals 4 minus x minus 2y. And then I'm going to substitute that thing into my function. So this thing will look like, in the end, x minus 1 squared plus y minus 0 squared plus 4 minus x minus 2y minus 2 squared. And I could FOIL that all out, or I could skip that step and just start taking derivatives. I'm going to vote for skipping that step and just taking derivatives. It'll probably fix itself. So let's give it a shot. I need an x partial of that function, and it looks like 2 times x minus 1 times 1 plus 0 plus 2 times 2 minus x minus 2y. So while I'm not going to FOIL out, I am going to simplify 4 minus 2. Just one fewer terms, it seems like it would be nice. So bring down the 2, reduce the power by 1. Chain rule says I should also multiply by -1 and set that whole thing equal to 0. And then simplify this mess a little bit. I'm going to divide everything by 2 because everything has a factor of 2 in it to get just x minus 1 minus 4 plus, nope, minus 2, because I said I was dividing all the 2's away, minus 2 plus x plus 2y, and that's equal to 0. Slide that over a little bit. Which ultimately gives me the equation 2x plus 2y minus 3 equals 0. There's my x partial, at least somewhat simplified. Let's go over to the other side. Look at a y partial. So I do need both. Oh, and what do I have from that y partial? I get 0 plus 2y plus 2 plus 2 times 2 minus x minus 2y. Chain rule says multiply by -2. And all that is equal to 0. And then do the same thing. Solving this mess. Again, I'll divide everything by 2 because I've got factors galore. This is y minus 4 plus 2x plus 4y equals 0. And if I reorganize everything, 2x plus 3y minus 4 is 0. Cool, I've got my system of 2 equations. I can see that I've just got 2 lines because both my x and my y's are linear. So if I'm solving a system of linear equations, I would expect exactly 1 point. Hi. Say that one more time? It was 5y. That is so true. I need to go back and fix my other notes. Yep. Yeah, that's a 5y. Yeah, they're definitely being added together. Crap. All right, well, that's fine. Again, I'm not very good with numbers. I assume that was all of the other hands I saw a second ago. Yeah, awesome. Okay, yeah, 2x plus 5y minus 4 is equal to 0. Does mean that the next part of this equation is a little less clean than the problem I solved earlier, but that's fine. At least this question or this answer will be more correct. I think I'm still looking to find just a single point, though. From a system of 2 lines, I'd expect 1 point of intersection. So I think I'll find just one critical point here. And I'm really hoping it's going to be a minimum, but I'll probably check that part too. So if I wanted to solve this thing, I'm going to get fancy with it. I do need to substitute from one end to the other, or a particularly common method we had for solving a system of equations was elimination, which is the one I'm going to use right here. I'm going to take my two lines, set them on top of each other, and just subtract one equation from the other one. And I like this method this time because I see a 2x show up in both of my equations. So if I just take their difference, the x part will go away. I'll just be left with a y value, which I think is 3y equals 1. And you can see if I had 3y instead of 5y, this solution would have just worked out to y equals 1, and it was a lot nicer than what we're going to deal with. But again, that's fine. This is correct anyway, so y is 1/3. Unless there's any shot that I screwed up the math earlier, but I don't think I did. Yeah. Okay, so y is 1/3. That's gonna be fine. I need to go substitute that back into one of my other equations. How about the one on the right? So this will be 2x plus 5 times 1/3 minus 4 is equal to 0, which means that x is going to be something kind of nasty. It'll be 1/2 times whatever that other number is. Figure it out. 5/3 minus 4 is 5/3 minus 12/3. 5 minus 12 would be -7. Add it to the other side, it becomes +7. Oop. So 7/6, if you buy that. Turns out the fractions I can get, but the simple addition is just too hard for me. Go figure. But all right, we've got almost everything we need now. We have our critical point. It's at 1/3, 7/6, 1/3. Say them in the right order. Jeez Louise. So we've got some things to go figure out. I should probably include something that verifies this thing is a local minimum. So I'm going to go find fxx, fyy, and fxy. Uh-oh, there's a lot of whispering out there. Oh, right. So my function, oh, right. No, fx, x, and fx and fy are right here. Fxx is 2, fyy is 5. And if I do the mixed, I get 2 again. Doesn't matter which one I do, it comes out to be 2 either way. So D, no matter where it is 2 times 5 minus 2 squared. And 10 minus 4 is 6, which is greater than 0. So I do have a maximum or a minimum, and if I look at both of my 2 second order straight derivatives, they are concave up. Concave up. Where again, I'm looking at that guy and that guy. Both positive, both concave up, so this thing is a local min. Local min. We'll highlight that guy too, and maybe, move you out of the way. How about over here? Because the last thing we might want to do is actually figure out what that local minimum is, which would just mean plugging some stuff in. So I know that z is 2 minus 7 over 6 minus 2 times 1 over 3. And that'll come out to a number, and then I can go figure out what it is. Let's see. What is that number? 2 times a third is 4, 6. 7 plus 4 is 11. Is that 11 sixths? 12 sixths minus 11 sixths is 1 sixth, if you buy that. So then the distance is the square root of 7 over 6 minus 1 squared plus y, which is a third minus 0 squared plus, what was z? It was 2, right? So is that 2 minus 1 sixth squared? Which ends up being some number. Uh, let's see. This will be 1 over 36 plus 1 over 9, which is 4 over 36, plus 11 over 36. Is that 121 over 36? Or square root 125 over 6. Square root of 125 is 5 root 5 over 6. I think that's smaller than the other number I got. But also, I did that on the fly. There could easily be a mistake in that number. I will, well, I'm sure one of you will let me know if I got it wrong. All right, wow, I'm way over on time. Sorry. Yeah, we'll end things here. I'll see you guys again on Monday. Okay, bye, 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 bye. All right. Fortunately, I hadn't hit the stop recording button yet. I just paused it. Because yeah, I was staring at this number at the end of class and realized that it didn't feel right. So there was another mistake in calculating the z value. Maybe you caught it already. We come over here to this equation, the thing we missed right here. That 2 was wrong. That was after I had simplified the z minus 2 part. This is on the equation of the plane itself, so this really should have been a 4. Let me mark this off in red because it's where I had to fix something after class. 4 minus x minus 2y. So we still had, what did we still have over here? We still have the minus 11 over 6, but this time it's 4 minus 11 over 6. 4, of course, being 24 over 6. If I subtract 11, I'm going to get 13 over 6 instead of 1 over 6. Because then, if I go look at this value right there, 13 over 6 minus 2, that difference is just going to become 1 over 6. 13 over 6 minus 12 over 6 is 1 over 6, meaning I simply have a 1 over 36 here on the inside of my square root, and then things simplify significantly more nicely. This is the square root of 6 over 36, which in turn is 1 over square root 6, or root 6 over 6. And that, I think, is a much better answer. Yeah, feels a lot more like a minimum. Anyway, there's that. So cool, cool, cool. Okay, bye, 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 bye for real. Bye, 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 bye.